So hardware tools for synchronization can either be used directly as synchronization tool. For example, if you're a kernel developer, you can use them directly, or they can be used as building blocks for other software-based synchronization tools. The first one is a memory barrier. So it is actually an instruction that makes any change made on one processor immediately visible to the other processor. The other thing that it does is make sure that all the load and stores are completed right before any following load and store calls or operations, right? So let's say an example. So if we have these two threads that we've talked about before, where one thread is simply printing the value of x when one thread is simply printing the value of x when the flag is true, and the other one is setting first the value of x to 100, then sets flag to true, right? So we said that in modern architecture, the order of instructions can be altered, right, for better performance. Now, if we insert a memory barrier in between these two loads and stores, then we make sure that each one of these will not be interrupted until the previous one is finished, right? So this means that the store right here, the x equal 100, will not be interrupted, right? It will first finish, then the next store of flag will be executed. So same thing here. This load operation will not be allowed to be interrupted until it's done, and then we move to the next load of the variable x. So as we said before, it is an effective hardware-based tool, and it can only be used by kernel developers because it's low-level operation. The other type of hardware-based synchronization tool is the hardware instructions. So these are usually the basic building blocks for the software synchronization tools which we'll be dealing with. So there are two main hardware instructions, the test and set and compare and swap. So the main idea behind these instructions is you are giving it a target value, right? And then what the instruction does is simply changing an internal variable to the new value, but returning the old value that you are trying to set. So if we read the test and set instruction right here, all it does is let's say we have this target right here, okay? So what we're doing is we're saving the old value of target, right, in this variable called RV, right? And then we are setting the new value of target to true, but we are returning the old value, okay? How would this be useful, and what are we going to use it for? So in the context of synchronization and critical section solution, what we could do is design something similar to this. So we could initialize a variable called false, called lock to false, right? And then implement the busy wait using the test and set instruction, right? So test and set for the first thread or process executing this code will return the old value of false, right? Which means that this thread will break out of the busy loop and enter the critical section. However, while this process is in the critical section and we have another process that tries to go in, now the test and set has been already set to true by P0, right? Because remember, in the test and set, we are returning the old value, but we are setting it to the new value, right? So for process P0, it had already set lock to false. I'm sorry, to true, right? So then the process P1 now will return true, but again set it to false, to the opposite. So since the return value here is true, then this process will not be allowed to proceed to the critical section. So it will hold in here, spinning and testing for the value of lock until P0 is done from the critical section. It will proceed to this line right here, which sets lock to false. And obviously what this will do is allowing the locked process or the waiting process to proceed to the critical section and so on. We can do something similar with the compare and swap, okay? So this one gives the kernel developers more flexibility, okay? Because it's dealing with integer values instead of booleans, right? But the concept is the same, okay? So you are still returning the old value of the variable, okay? And you are testing it against an expected value and setting it to a new value. And this is an example of how would that be used in a critical section solution scenario. Again, you have a lock that is initialized to 0. You are testing it against this value and setting it to this new value, okay? But you are still returning the old value, which means that the first process to execute this will break and enter the critical section, but the next one will hold in this while loop, which ensures mutual exclusion. So this is a one full solution that could work for n processes using the compare and swap. So we know that the compare and swap makes sure that we have mutual exclusion, the first condition, right? And then the next one, which is progress, which means we are simply allowing every waiting process to eventually get a chance to enter the critical section, and this is ensured in this block right here, which is the exit section. So this simply means that every exiting process is looping here in the waiting array. So here, if there is any process that's currently ready and it is waiting for its turn, it will set its waiting flag to true. So the exiting process will spin and search the entire waiting array to allow the first process found to enter the critical section, okay? So if there is none waiting, then we will simply set lock back to 0 just in case a process comes in the future and tries to enter the critical section, okay? And also, the exiting process will set its own waiting flag to false, which means that I'm done, I'm exiting, I do not need to enter the critical section at this point. For the bounded wait, since we have n processes and every exiting process will be searching the entire n position array, then the worst case scenario, every process will have to wait for n-1 turn to enter the critical section. So we do have a bounded wait. Therefore, since this satisfies the three conditions, so we can say that this is a critical section solution.